Alright, so in this video I'm gonna be explaining another important article with the title Graph Neural Networks with Maximal Independent Set-Based Pooling, Mitigating Over-Smoothing and Over-Squashing. This paper in 2025 in the Journal of Pattern Recognition Letters. Graph neural networks have significantly advanced graph-level prediction tasks by utilizing efficient convolution and pooling techniques. However, traditional pooling methods in GNNs often fail to preserve key properties, leading to challenges such as graph disconnection, low decimation ratios, and substantial data loss. So we introduced three novel pooling methods based on maximal independent sets to address these issues. Additionally, we provide a theoretical and empirical study on the impact of these pooling methods on over-smoothing and over-squashing phenomena. Our experimental results not only confirm the effectiveness of using maximal independent sets to define pooling operations, but also demonstrate their crucial role in mitigating over-smoothing and over-squashing. So over-smoothing refers to the phenomenon where node representations converge to vectors whose values are independent of initial node features. And over-squashing is the GNN's inability to transform information between two distant nodes. However, as the depth of the network increases, the size of receptive fields increases exponentially, causing distant nodes' information to be squashed by information from other nodes. So consider a sequence of graphs produced by GNN. For a given layer, we define a reduction window of V as a set of vertices used to compute the feature of V at layer L. Additionally, we assume that for any V, that reduction window constrain the reduced graph like this. So in other words, two adjacent or overlapping reduction windows at layer L-1 induce adjacent vertices at layer L. If the set of reduction windows computed at any level forms a partition, then the set of receptive fields forms a partition. And they have a proposition that says given a sequence of reduced graphs built by alternating one-hop GSO convolutions with top K pooling, we have the following property. At any level, two vertices are non-adjacent if and only if their associated receptive fields are disjoint and non-adjacent. But what is this maximal independent sets and how is it related to graph pooling? We consider a finite set with a corresponding neighborhood function defined on X such that each element of X is its own neighbor. A maximal independent set is a subset that satisfies just these two conditions. The elements of J are referred to surviving elements or survivors. And equation 5 specifies that two adjacent elements cannot both be selected or survive at the same time. Now, equation 6 guarantees that at least one surviving element exists in the neighborhood of each non-surviving element. From a subsampling perspective, these two equations prevent both oversampling and undersampling, ensuring a uniform distribution of surviving elements throughout the structure. So this maximum independent set can be computed using, this is a very old, maybe 1980, and a very old algorithm. A specific value is assigned to each element within the set if If J denotes a current independent set of X, Muir's algorithm iterates over the set where n of J denotes the neighbors of J until the independent set becomes maximal. More precisely, for each iteration, the vertex X is added to J if V sub X is maximum among X neighbors not in n of J. The algorithm concludes that when it is no longer possible to add any remaining nodes to J without violating these two equations 5 and 6, and by construction each element represents a local maximum at a particular iteration. Now we're related to graph pooling here. We introduce MIVS pool, a pooling method based on maximal independent set defined on the graph vertices. So a similar method was proposed in 14 using a MIS computed on the K-hop neighborhood. This method assigned a learnable projection score to each vertex to select the most relevant one for a specific task. However, if two adjacent vertices have identical scores, the selection becomes indeterminate. An alternative strategy is to merge similar nodes, reducing information loss from combining the similar vertices. Since each level of the hierarchical pooling represents a level of abstraction from the initial graph, we define a similarity score between two vertices at level L. Well, W is a learnable matrix. So for center U of star, we generalize this 7 and set the new attribute of U as the sum of the attributes associated with each selected edge incident to U. This sum is normalized by the total of the similarity scores of all selected edges incident to U. Because if you have an incident isolated edge like E of UV, they are both of them play a symmetric role. That's why we arbitrarily assume that U survives at the next layer. Its features are set to and each one is like trying to make it symmetric. And then they call the MIES cut, which performed 3 operations: the computation of maximal weight matching, the assignment of nodes not incident to a selected edge, and finally the splitting of path of length 3 into 2 isolated edges. Instead of these 3 steps, we propose to adopt the maximal independent directed edge set reduction scheme as suggested in this reference. This reduction scheme allows us to avoid splitting of path of length 3. To do this, we need to consider oriented edges and split an edge into 2. At layer L, for each edge, their neighborhood corresponds to every edge either leaving U or V or arriving at U. So if we compare the neighborhoods of 9, this neighborhood, and that of MIES, the major difference is that MIDES excludes edges heading towards V in its neighborhood, leading to an asymmetry in selection and therefore creating stars centered on V. Indeed, computing a MIS on a directed edge set with particular neighborhood is one of the 2 main principles of MIDES algorithm. And then they did it for these data sets D&D, NCI 109. And you see that if you combine it with GCN, this is much better than other combinations. Also, their model is better than edge pool, 1%, and it is better than SAG pool, 3%. It is better than GCN and G pool, 6% improvement.